everyone, I'm Sujani, Faculty in Physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to have a discussion on tutorial question bank. So we are going to discuss all the questions related to Module 1, that is Introduction to Quantum Physics. So before going into the discussion on the question bank, let me tell you about the assessment with regards to this course. We are talking about the course Engineering Physics at the first year level. So in this course, we have assessment divided. We have the assessment divided into 3 parts. First one is CIE, which will be for 20 marks. Then we have AAT for 10 marks. And then we have SEE for 70 marks. And the total put together is for 100 marks. So the course which we are talking about is Engineering Physics. And the assessment will be for 100 marks by the end of the semester. And how it is done, I have explained, divided it into parts. I will explain each one to you very clearly so that you will have a clear idea before you do the course. So the first one is CIE. So what is CIE here? CIE refers to Continuous Internal Evaluation. Continuous Internal Evaluation. So in a semester, you'll have 2 CIEs. CIE 1 will be after completing at least 20 to 25 hours of instructions. After 20 to 25 hours of instructions are over, you will be having CIE 1, and the CIE 1 will be for 20 marks and it will cover the first 2.5 modules. The entire curriculum is divided into 5 modules. So in CIE 1, you'll be having the 2.5 modules, means module 1, module 2 and the first part of the third module also. And again you will have CIE 2 during the end of the semester. After completing all the 45 hours of instructions, you will again have a CIE for 20 marks. This will cover the rest of the modules, rest of the 2.5 modules, means the second part of the third module, 4th and 5th module. So this is how the CIE is conducted, and the average of these 2 marks we will take for final CIE. So these 20 marks will come from the average of CIE 1 and CIE 2. So both the CIEs are very important, and now you understand how it is divided. Now come to the AAT. AAT stands for Alternate Assessment Tools. AAT is Alternate Assessment Tool. So in Alternate Assessment Tool, we have many things. We have assignments, we have quiz, we have concept videos and tech talks. But for this particular course, you have tech talk for 5 marks and concept video for 5 marks. So total put together will be for 10 marks. So the AAT will be for 10 marks. So what is there in this tech talk you need to know? So tech talk and concept video are aimed for holistic development of the students. So by involving in these 2, you will learn how to search for information, how to gather information, and how to present information. See, the first thing is tech talk. there will be around 500 topics that will be uploaded in your CMS portal, which are taken from the latest journals and reputed journals. So you can select any one topic from that and give a tech talk on it. So you can search for information related to that topic and prepare a PPT, PowerPoint presentation, and present it in front of your evaluator or in front of the faculty. And then you have the concept video. Again, in concept video also, we will be uploading the topics in your CMS login. You can select one topic. Most of the times, these topics are related to your curriculum, an extension of the topic which is there in your curriculum. So you will select a topic, you will prepare a PowerPoint presentation, and you will have to make a video of it. So by doing this, you will learn the skills of presentation skills and also the communication skills. So these alternate assessment tools are helping you in gathering the information, updating yourself on the latest technologies, and also you will improve your presentation skills as well as your communication skills. So this is about AAT. And the third one is SEE. So SEE stands for Semester End Examination. Semester End Examination, which we call it as SEE. So this SEE will be for 70 marks, and I will discuss how the pattern of this SEE paper will be. We will discuss both CIE paper as well as SEE paper so that you will have a clear idea when I'm discussing the question bank. You will come to know which type of questions will be asked in CIE, what will be the weightage, and also what type of questions will be asked in SEE and their weightage too. So let us first look at the CIE paper. CIE, as I told you, it is a continuous internal evaluation paper. I said we have two. So the pattern is the same for both CIE 1 and CIE 2. Only thing is we are taking the average of the two at the end. So the maximum marks for each CIE is 20, and the time we'll give you to answer is 2 hours. So what you have to do here is you have to answer any 4 questions out of 5. You will be given 5 questions. I told you the syllabus will be 2.5 modules. Say for the first CIE, for CIE 1, what you will have is from module 1, you will have 2 questions. From module 2, you will have 2 questions. And we are covering only half the module of the third one. So from the third module, you will get 1 question. So total there will be 5 questions, out of which you have to answer only 4, any 4 questions. Okay, so this is clear. So if you are preparing for 2.5 modules, well, you can very easily answer the 4 questions. And what is the weightage for each question? So if we take the first question, there are 2 parts. In every question, there will be 2 parts, A and B. So the A question will always be a theoretical question. So where you will have to explain, describe, or discuss things over here. And the B part will be analytical question. This will be an analytical question. So the theoretical question is for 2 marks and the analytical question is for 3 marks. So each question carries 5 marks. Each question carries 5 marks. So you will be writing 4 questions. So 4 into 5, 20 marks. As simple as it is. So in each question, what you are doing, you are answering 1 theoretical question and 1 analytical question. So 2 plus 3, 5. So 4 such questions will give you 20 marks. So I hope this CIE pattern is clear. So when I'm talking about 2 marks question means most of the times you will be getting short answer questions here. And then analytical questions which are simple, not so complex, that you will be getting for 3 marks. So theoretical as well as analytical both are taken care of. Now coming to the SEE paper. SEE, semester and examination paper. It will be for 70 marks as I said, and the time given will be 3 hours. And how the questions are given is, from each module you will be given 2 questions, 1 and 2, and in each question there are subparts A and B. Here you have to answer any one question from each module. How is the pattern here? From each module you will be given 2 questions, and from the 2 questions you can answer any one. Means you are answering one question from each module, and as I told you, each question is subdivided. So A part is for 7 marks, which will be a theoretical question, and B is again for 7 marks, which will be analytical. So in both the papers, we are covering theoretical as well as analytical questions. So in the same way, in module 2 also, you'll have 2 questions, out of which you have to answer 1. So we have 5 modules. So 5 questions we have, which you will be answering. Means you will be having an internal choice. In the module itself, you will have an either or question, that or this. So you will be answering 5 questions, and in 5 questions you have part A and B also. Each part is for 7 marks. So one question, each question is carrying 14 marks. Part A for 7 marks and part B for 7 marks, so 14 marks. So 14 questions into 5, you will get 17 marks. And now when I say each question is for 7 marks here, the theoretical question will be a long answer question, and the analytical question may be a little complex. You may have to deduce some relations and then calculate the values and apply them. So I hope with this in mind, we can easily go and discuss the question bank. So now let us move on to the question bank. First, we'll be discussing the short answer questions. So in this discussion, I'm not going to explain you the full answer. I'll be just briefing you what are the points you have to cover regarding that question. And if you have any doubts, or if you want to get the answer for that particular question, you can refer to the video related to that concept. We have already uploaded the videos regarding the entire module. So whatever topic you want the answer, you can refer to that particular video and get the answers. So let us move on. First question, relate quantum mechanics with classical mechanics. So it is a short answer question. We have to just write point wise. So for a few questions, I'll tell you so that you will have an idea of how to write the answer. So quantum mechanics is a branch of physics dealing with the behavior of matter in light and the atomic and subatomic scale. For quantum mechanics, this is very important. Then what is classical mechanics? Because we have to relate quantum mechanics with classical mechanics. So classical mechanics is a branch of physics which is based on Newton's laws of motion, and it is applicable to systems which are large, which are macroscopic. So this is the major difference between quantum mechanics and classical mechanics. In quantum, we are dealing with microscopic objects. Here it is macroscopic. So what is the second question? What is quantum mechanics and what does it explain? So quantum mechanics is the branch of physics, and it helps how it interacts, the matter interacts. And also it explains about the behavior of atomic and subatomic particles. Next, what is de Broglie hypothesis of duality of material particles and the concept of matter waves? So Louis de Broglie is the name of the scientist. In the year 1924, he made a very bold suggestion. That is why we call it as hypothesis. There is no background or no experimental evidence. He just put his thought or a logical mind he applied, and he just gave a hypothesis which said, if radiation, which is a wave, can exhibit particle nature. When we are talking about radiation, it is a wave, but it is exhibiting particle nature under certain circumstances. And since we know nature likes symmetry, he said particles should exhibit wave nature under suitable circumstances. So this is the logic he has brought forward. When radiation, which is a wave, can behave like a particle, so the particles also should exhibit wave nature under certain circumstances. So this is how we are relating the particle and wave nature. Now the next question. Show how de Broglie wavelength is expressed in terms of momentum and kinetic energy. We are going to write the de Broglie wavelength lambda in terms of momentum. So we write it as h by p or h upon mv. And then we also write it in terms of kinetic energy as lambda is equal to h upon under root 2me, where E here represents the kinetic energy. So if you want the proofs, you can refer to the videos and then understand how we are deriving them. Then extend the equation E is equal to h nu and derive the de Broglie relation. The same thing with what we are talking about h upon mv, we are getting from E is equal to h nu. So how we are deriving the equation? So we have to start from E is equal to h nu, and then this is according to Planck's theory. We have E is equal to mc square according to Einstein equation, and we are equating both, and then we get hc by lambda is equal to mc square, and relating or rearranging the terms, we get lambda is equal to hc upon mc square, and then we get lambda is equal to h upon p or h upon mv. So what they're asking us, how do you get the formula for lambda from E is equal to h nu? Now the next one. Relate the concept of light radiation with wave particle duality. Means we are talking about light radiation and how does it have wave particle duality. So radiation has dual nature. It is a wave and spread out over space. Whenever we are talking about the propagation or when we talk about the phenomenon of interference diffraction, we talk about the wave nature of radiation. But under certain circumstances or to explain certain phenomena like black body radiation or the photoelectric effect, we use the particle nature. So when we say particle, a particle is localized in space. So that is how we are using the wave particle duality. Both the natures we are considering. The next question, what are the two concepts taken into consideration to arrive at de Broglie's wavelength, which we have already discussed? So the first one is E is equal to h nu, which is the Planck's relation. And the second one is E is equal to mc square, which is the Einstein's relation. So we are using these two relations to get our de Broglie wavelength. Lambda is equal to h upon mv. Now write the different forms of de Broglie wavelength. So what are the different forms we have to write the de Broglie wavelength? So de Broglie wavelength lambda is equal to h upon p, or p is nothing but momentum. So we can write it as mv is equal to h upon mv, or we can also write it in terms of energy. So h upon under root 2me, where E represents the energy, or we can also express it in terms of potential, the potential that is applied. So 2meV, where E is the charge and V is the potential applied. So these are the different forms of de Broglie wavelength. Next, what is a wave function and what are its applications? So let us see what is a wave function. So wave function psi, it has no direct physical meaning. It is a complex quantity representing the variation of matter wave. So whenever we have to represent a matter wave, we represent it with the help of a wave function. That is how we define a wave function. So what is the application of this wave function? Suppose a quantum particle is confined to a one-dimensional potential box of width L. And we know that it is in its first excited state. If you know the energy in the first excited state, we can determine the probability of finding the particle at any position. This can be applied to electrons in a metal. So that is how this function, wave function, has become very significant. Now the next one is normalization condition. So what is normalization condition? So when we are talking about a wave function, as I said, it is a complex quantity. When you have to find the probability of finding it, what we do in a given space is, we always multiply it with its complex conjugate. So if you know psi x, you multiply it with psi star x, so that it becomes real. So when you are having psi star, and if you want to know the probability of finding it in a certain area or a certain region, when you integrate it over the entire area, the probability of finding it should be 1. So integral of psi star psi. Psi here is a function of x-ante, means it's varying with time and position. So here it is equal to 1, means the maximum probability is 1. So this we are calling it as the normalized condition. So a wave function is said to be normalized if it satisfies this condition. So if this condition is satisfied, then it is normalized. Now explain the physical significance of wave function, which we have already discussed, the wave function. Next, list any two properties which reveal the behavior of matter waves. So we are going to discuss the properties of matter waves. So de Broglie wave or matter wave is independent of the charge. It is not dependent on the charge. So they are not electromagnetic waves, we say. And de Broglie wave is associated with every moving particle. Because when we are talking about lambda is equal to h upon mv, if the velocity is 0, lambda will be equal to 0. So only with moving particles it is associated, whether they are charged or uncharged. So these are very two important properties of matter waves. Next is the time independent Schrodinger wave equation. So whenever we have to express the wave function, so we use the Schrodinger wave equation. So what is the Schrodinger wave equation? Dou square psi by dou x square plus 2m into e minus v by x square into psi is equal to 0. So here we are discussing the short answer question, so they will not ask you to derive. You may only have to explain the terms that are involved in this. So what is psi? Psi is the wave function. M here is the mass of the particle. If you are talking about the electron here, it will be the mass of the electron. E is the energy and V is the potential. And H cross is H upon 2 pi, where H is the Planck's constant. So if you explain all the terms, and if you want to write the expression for energy from this also, you can take the terms onto the other side and write it as minus h square by 2m dou square psi by dou x square psi of x plus v of x. Here we are writing it as a function of psi. Now, what is the principle on which Davison and Germer experiment works? So, Davison and Germer's accidental discovery of the diffraction of electrons was the first direct evidence. So, it works on the principle of diffraction of electrons. So, when he did the experiment on a nickel crystal, when electrons were bombarding, they are diffracting, means they are getting diffracted at different angles. So he measured the angles and he calculated the wavelengths, and thus he arrived at a very important conclusion or a direct evidence for their wave nature. So it depends upon the diffraction of electrons. Now, discuss the experimental setup. So here you need not explain the whole experiment in short answer. They are just asking you to explain or draw the experimental setup. So in the experimental setup, what we have is an electron gun. Okay, so there is a filament and to which we are connecting a small battery. So when this is on, the filament gets heated and the electrons are emitted by means of the thermionic emission. And these electrons are collimated with the help of this collimator. So you will keep slits like this so that there is a fine beam. Otherwise, the electrons are coming out in all the directions. So now this beam is coming and hitting a nickel target. This is the nickel crystal we are taking. So when it hits, what happens? There is diffraction. So they will diffract at different angles, and the diffracted beam is captured with the help of a movable detector because they are diffracting at different angles. So we'll have a detector which can move on a circular scale, and everything is kept enclosed in a vacuum chamber. So just to prevent the oxidization on this nickel target. And also to make these electrons move fast, we are maintaining a very high potential with the help of this. So we are maintaining a potential between the target and this very high so that the electrons will be accelerated. Now next one, summarize the observations in Davison and Germer experiment. So what are the observations he made and what are the conclusions? In the next question, we are going to discuss the conclusions. So what are the observations? What he observed is, with the intensity of the scattered electron for an accelerating voltage of 54 volts and scattering angle theta is equal to 50, the peak for intensity, there is maximum intensity, the strong peak for intensity. So what is the applied voltage? 54 volts. And what is the angle at which they are diffracting? 50. So this peak was the result of constructive interference of the electrons that are scattered from different layers of the regularly spaced atoms in the crystal. So this is his first observation. So after observing this, he assumed that it is maybe because of the constructive interference. And with the help of electron diffraction, the wavelength of matter waves was calculated and it was found to be 0.165 Newton meter. So after getting these two values, he substituted them and theoretical values and he got it as 0.165 nanometer. Now, what are his conclusions? They are the observations and these are the conclusions. So, what are his conclusions? According to de Broglie relation, electrons with kinetic energy of 54 electron volt have a wavelength of 0.168 nanometer. And the experimental outcome means he calculated the wavelength using lambda is equal to h upon under root 2 MeV. So we have got the voltage. So apply the voltage, the mass of the electron, the charge of the electron is known, h is constant. So he has got 0.168 nanometer. And the experimental outcome means he used the Bragg's law 2D sine theta is equal to n lambda. So at 54 volts, the angle is 50 degrees. So he used this and he calculated and it is 0.165 nanometer. So they are approximately equal. So that is how they closely matched with the predictions. Now for the particle in a box, we have to give the expression for the wave function as well as the energy. So the wave function in 3 dimension is always given by psi of r. So when I say psi of x, it is always in one dimension. Means I'm talking with respect to only along one axis, psi of x in one dimension. But when I say psi of r, it is with respect to all the three axes we talk, x, y and z. So this is 3 dimension. So in 3 dimension, it is represented as psi of r, and that is a is equal to sine kr, and we know all the values. And from here, we have derived the expression for energy. E is equal to n square h square upon 8ml square. N is the order or the level, h the Planck's constant, and the mass, and L is the length or the width of the box. Now explain the assumptions for the electron to consider it in a potential well and arrive at Eigen Functions and Eigen Values. So we have to explain how we are arriving at the Eigen Functions and Eigen Values. So what are the assumptions here we are taking? If you see here, this is symbolizing an electron which is trapped in a metal. So a free electron trapped in a metal, or the charge carriers, for example, which are trapped by potential barriers, can be approximated to an electron in a deep one-dimensional potential well. So this is the situation. So what are the assumptions that are made? The movement of electron is restricted by the sides of the wall. So you can see the electron can move only till here. Otherwise, it cannot move ahead because of the restrictions of the wall. And the electron moves only in the x direction. We are talking about the movement. One dimension, we are talking only about the x-axis. We are not talking about the vertical motion. So we are talking about the second assumption. Then there is elastic collisions with the walls. Elastic collision, when I say, there is conservation of energy. Then the potential energy V inside the box is 0 and stays constant throughout the length. So this electron is moving in a constant potential well. That is the next assumption. Then V is high outside. The potential here is maximum. We say it is infinity. That is why the electron cannot cross this barrier and come out. So all these are assumptions we have considered for an electron trapped in a metal. Now the wave functions and energy. So the wave functions and the corresponding energies, which we always call as the Eigen Functions. So the wave function is nothing but the Eigen Function, and the corresponding energies are the eigenvalues. So whenever we are describing a quantum state of the particle, when I talk about eigenfunction, it is the wave function of that particle, and the eigenvalues are the energies that are related to that particle. So wave function is represented as psi of x is equal to a sine kx, and the energy is represented by n square h square upon 8m l square. So now coming to the long answer questions. We have already completed 20 short answer questions, which we have discussed almost in detail. Now for the long answer questions, as I told you, I'll not be discussing the entire question. I'll be giving you the key points which you will have to cover for, because it will be a 7 marks question. So what all you have to write to score 7 marks, because we have still not got away with our marking scheme. So marks are also important when you are writing the questions. So what are the key points in the introduction to quantum mechanics? So all the points that are related to quantum mechanics. The first thing, it is always talking about microscopic particles. So wherever classical mechanics failed, means regarding the explaining the behavior of the microscopic particles like protons and electrons, how quantum mechanics could successfully explain. And then the black body radiation, the photoelectron effect, and the quantum effect, the Compton effect, which helped in strengthening the quantum mechanics, which you have to discuss. Then, how quantum mechanics paved the way for better understanding of matter than classical mechanics, explain. So these two are related questions. Only thing is asked in a different manner. Then compare a particle with a wave and discuss about the dual nature of radiation. So first you have to talk about what a particle is. When I say particle, it is localized in space. When I say a wave, it is not localized in space. So for explaining certain phenomena, we consider the wave nature. Like interference, diffraction, I said, we'll be considering the wave nature. But to explain certain phenomenon like photoelectric effect, we consider the particle nature. And so both these natures are essential in explaining the concept of radiation. So we consider the dual nature of radiation. So you'll have to elaborate all these points and write. Then explain Max-Born interpretation of the wave function. We have to explain the Max-Born interpretation means the physical significance of the wave function. So you will have to write down all the significant points regarding the wave function. Wave function is a complex quantity, does not have any physical significance. To make it real, we multiply it with a complex conjugate. And in order to find the probability of finding a particle, we try to normalize it. The normalization condition is given by psi star psi. And if psi star psi is equal to 1 means the probability of finding it is in that particular region. So like that you will have to write all the points regarding the physical significance. Then explain how to arrive at an expression for the wavelength associated with an electron accelerated by the potential. So here you will have to derive the entire expression starting from E is equal to h nu and considering the other equation E is equal to mc square. Using both, how do you arrive at lambda is equal to h upon mv or h upon under root 2 mev? You will have to do the entire derivation. Arrive at the expression means you will have to derive it because it's a long answer question for 7 marks. All the steps you have to write. Then show that the expression for the wavelength associated with an electron in terms of mass m and velocity v is lambda is equal to h upon mv. So again the question same is asked in a different manner. So it is lambda is equal to h upon mv. You are going to derive how you are getting it. Then summarize the de Broglie concept of matter waves. So what is de Broglie concept? So first we'll have to explain what all he considered. So the bold suggestion or the hypothesis that he has put forward, first you have to state. Then you will have to explain what nature of particle we can consider particle nature and where we can consider it as a wave nature. So step by step you will have to explain the de Broglie's concept. Next, relate different properties of matter waves and describe the concept matter waves are not electromagnetic waves but a new kind of waves. So here again, we have to write all the properties of matter waves starting from first one, they are not electromagnetic waves because they are not associated with charged particles. Second thing, only moving particles are associated with the de Broglie wavelength. So if the velocity is 0, then there is no wavelength. So it is associated with moving particles. They are not electromagnetic waves. So whether charged or uncharged, they have a de Broglie wavelength we can write if you know the velocity of the particle. And then again, you can also derive the expression for angular velocity, which shows that they move with a velocity greater than the velocity of light. So, which is not possible. So, matter wave representation is only a symbolic representation. So, you will explain all these points with relate to properties of matter. Next, to show that the wavelength associated with an electron of mass m and kinetic energy E is given by h upon under root 2 me. So, you are going to derive this expression lambda is equal to h upon under root 2 me. All the steps you have to write. Write from E is equal to h nu, E is equal to mc square, substitute, simplify, derive, and then you will arrive at this expression. Then you can refer to the video on de Broglie wavelength, then you will get the expression for de Broglie wavelength. Next, show that the wavelength associated with an electron of mass m and kinetic energy E is given by h by p by making use of Planck's Einstein theory of radiation. So again, for deriving all these, we are making use of Planck's Einstein theory and the Einstein's theory of relativity. Next, summarize the construction of Davison and Germer experiment and explain the use of each component broadly, because it's a 7-mark question. So first thing what you have to do is draw a neat sketch, the diagram you have to draw, showing the experimental setup. So then what you have to do is explain the setup or explain the different components that are there in the setup. You will have to explain. And the third thing is the procedure of how we are doing the experiment, how the electrons are emitted, how they bombard the nickel crystal, how they are diffracting, and how do we collect them with the help of a detector and measure the angles. And then comes the observations from the experiment. What are the observations? What was observed? Where was the peak we are getting? That we have to write. And then the conclusions. So what are the conclusions that are drawn by Davison and Germer, which helped in establishing the wave nature of electrons? So these are the steps you will have to follow to explain this Davison and Germer experiment. Then 12th question, how did Davison and Germer in their experiment explain the proof for wave nature of electrons? So when it comes to the proof, here we have to explain what are the theoretical values. Theoretically, we have lambda is equal to h upon under root 2 MeV. So at a voltage of 50 volts applied, what is the value of lambda we are getting? And experimentally when we are doing, we are seeing a peak at a voltage of say 54 volt. See here, this is approximately I've written, but 54 volt, and the angle is 50 degree. So at this, how are we calculating? Using and lambda is equal to 2d sine theta, Bragg's law. So both you have to explain here and explain how he has concluded about the wave, because both the theoretical and the experimental values are matching. So he has concluded that these particles must be exhibiting wave nature. Then show that the expression for the wave function for the wave associated with the moving particle psi is given by a exponential minus I upon h et minus px. So whatever expression we have derived in time independent Schrodinger wave equation. So the solutions of the Schrodinger wave equation give us the wave function. So derive the expression first and then arrive at psi. Then 14th question. Extend the concept of dual nature of electron to arrive at Schrodinger's time independent equation. So in short, you will have to derive the Schrodinger's wave equation. What we have derived, dou square psi by dou x square plus 2m into E minus V upon H cross square psi is equal to 0. This is what we have to derive. But here you have to start with the concept of dual nature. So in the dual nature, what we have taken is psi of x is equal to a sine omega t minus kx, because we have considered the wave nature, and we have also considered the wavelength lambda as h by p or h by mv, and then we have considered the energy, the total energy E will be equal to k plus v, the kinetic energy plus the potential. So the kinetic energy can be written as E minus v, and so using these two we are getting this expression. So the entire derivation, you can refer to the Schrodinger time independent equation video to get the entire derivation. You can understand it. Next, show that the permitted energy levels of a particle are given by n square h square by 8 ma square, assuming that m is the mass of the particle confined in a field of free region, and the limits are x is equal to 0 to x is equal to a. So in short, here we are deriving this expression E is equal to n square h square upon 8ma square. So m is the mass, a is the limit. We have seen that the potential box, the limits are from 0 to a. So derive the expression for E. So that is the application, one-dimensional potential box problem. Next, interpret the results from the eigenvalues and eigenfunctions and the probability density for a particle in one-dimensional potential box of infinite height. Also sketch the figures. So as I told you, eigenvalues means the energies. Eigenfunctions are the wave functions. So what is the wave function and what is the corresponding eigenvalue? So you are going to discuss for different levels, and also you have to sketch the figures. So when we are talking about, suppose I talk about a wave function at the initial level, n is equal to 1. So maybe I will have a wave function at n is equal to 2. So what are the energies corresponding to them and how the waveforms are going to change, we are going to discuss. So you can refer to that particular video to understand these sketches also. Then summarize the conclusions of the applications of Schrodinger's wave equation on an electron in a one-dimensional potential well. So what are the conclusions that we are drawing from the Schrodinger wave equation on an electron in one-dimensional potential well? So you will have to summarize everything, what we have to recall, what we have done for the eigenvalues, eigenfunction, then probability density of the wave function, and then how we applied it for a one-dimensional potential box. So we'll have to understand everything and then summarize them. Now let us do the analytical questions. So as told you, when we have discussed the paper, I said the first part is always a theoretical question. When it comes to CIE paper, you may get short answer questions. When it comes to SEE paper, you will get the long answer questions. Then these analytical questions are common for both. In both you are having in part B, you have analytical questions. So, and the weightage for these questions is also more. Now, the first question, calculate the velocity and kinetic energy of an electron having wavelength of 0.21 nanometer. Here also, I am not going to solve the numerical because we have videos on numericals. Especially if you are talking about de Broglie wavelength, you will find a entire video on numericals on de Broglie wavelength, numericals on potential box. So for solutions, you can directly refer to that. Here, I'm just going to give you the outline, how you approach the problem and how you solve it. So when it comes to this problem, whenever you have to do a numerical, an analytical question, what you have to do first is, what is the data given? The first step is to write the data given. Means what is given and what you have to find. Then you will have to look for an appropriate formula. So if you have a formula directly, you can use it, or you will have to deduce the formula. Deduce the sense, we have the formula for de Broglie wavelength. Lambda is equal to h upon mv. But I am asked to calculate the velocity and not the wavelength. So I will write v is equal to h upon m lambda. As simple as it. So we are just transposing and getting the formula for v. V is equal to h upon m lambda. So write the formula, and the next thing is substitute. Substitute the quantities in the given formula. But before substitution, you will have to take care of the system which we are following. Usually we see that all the quantities should be in a single system of units. So mostly we'll be using the SI system. After substituting, you will simplify and then you get the answer result. Along with units, you also have to mention the units. So these are the things you will have to keep in mind whenever you are doing the analytical questions. So in this particular question, we are given lambda. You have to find the velocity. So V is equal to h upon m lambda. We'll use this formula. H is a constant, 6.625 into 10 power minus 34. M, mass of the electron, is constant, 9.1 into 10 power minus 31. And lambda is given. It is given in nanometer. So the system we have to remember, 1 nanometer is 10 power minus 9 meters. So do the conversion, substitute and get the answer for the velocity. So if you have to calculate the kinetic energy is given by half mv square. Once you get the value of V, you can easily calculate the kinetic energy. Next question. Find the de Broglie wavelength associated with a proton moving with a velocity of 1/10 of the velocity of light. So how do we do this? First, as I said, write the data given. Then write the formula. Once you write the formula, do the substitution. After substituting, you can use your calculator to get the answer. So this is the answer. So the de Broglie wavelength is given by 1.322 into 10 power minus 14. So here what you have to focus is the velocity is 1/10 the velocity of light. So you should know the constant. What is the velocity of light? Substitute it here and get V and then do the normal substitution. Next, calculate the wavelength of an electron raised to a potential of 15 kilovolts. So kilovolts. So which formula we'll use here is lambda is equal to h upon under root 2 MeV. Because we have to calculate the wavelength and we are given the voltage. So, or the potential is given as 15 kilovolt. So, here the conversion you have to do to volts because it is given in kilovolt. So, the standard unit in SI system is volt. So, we will convert it into 15 into 10 power 3 volt. And the charge of the electron is also constant, 1.6 into 10 power minus 19. The mass is also fixed, 9.1 into 10 power minus 31 kg. So get all these values, substitute and simplify, you get the wavelength. Next one, find the de Broglie wavelength of neutron. You also have to read the question carefully and understand what you, till now we have been finding for electron. Now we have to find for neutron, given the kinetic energy and the mass of the neutron. So how are we going to do it? So first write the data given. Kinetic energy is given. We are converting it into joules because it's given in electron volt. You need to know the conversion from electron volts to joules. 1 electron volt is 1.6 into 10 power minus 19 joules. And the mass of the proton is also given. So which formula we are going to use? Lambda is equal to h upon under root 2 ME because the kinetic energy is given. So substitute and you get the answer. You will do the substitution and simplify it. You get the answer maybe in angstrom or in meter units. Next, calculate the velocity and kinetic energy of an electron of wavelength 1.66 into 10 power minus 10. So here the wavelength is given and you have to find the velocity. Wavelength is 1.66 into 10 power minus 10. So we have lambda is equal to h upon mv. So v will be equal to h upon m lambda. So always remember the standard formula. From that you can find any relation. So lambda is given, h and m are constant, so you can easily get the value of v. Then find the wavelength associated with an electron rose to a potential of 1600 volt. So here we will use the formula lambda is equal to h upon under root 2 MeV because the voltage is given. We are using different forms of the formula. We have already discussed different forms. So just to substitute for voltage as 1600, all the others are constant. So we'll get the value of lambda. Say V is given. Lambda is equal to 12.26 under root V. We can use this formula also directly, because when I'm telling you the formula lambda is equal to H upon under root 2 MEV, H is a constant, 6.625 into 10 to the power of minus 34 joule seconds. The mass of the electron is constant, 9.1 into 10 power minus 31 kilograms. The charge of the electron is constant, 1.6 into 10 power minus 19. Of course, 2 is a constant. So by substituting all these values, we can find H upon under root 2 ME. This gives us 12.26. So we are left only with under root V. So we are using it directly. Means the value of this is, I'll not write this, the value of H upon under root 2 ME is 12.26 angstroms. That is why we are writing it in angstrom. So after substitution, we are getting the answer also in angstrom. Next, calculate the energies that can be possessed by a particle of mass 8.5 into 10 power minus 31, which is placed in an infinite potential box of 10 power minus 9. So let us see first the data. What is the data given? Mass is given, L is given, H is a constant. We have to find it for N is equal to 1 first. So what is the formula we are using? En is equal to n square h square upon 8m L square. So just substitute and simplify, you get the answer. So write the data correctly, use the appropriate formula, substitute and get the answer. So they have asked calculate the energies. So we will calculate it for the first excited state also. If this is E1 for the ground state, E2 will be for the first excited state. So for the first excited state, our n will be equal to 2. So n square will be equal to 4. So whatever we are getting here, we are multiplying it with 4. So that we get the answer for the first excited state. Now the next one is, an electron is bound in one-dimensional box of side 0.1 nanometer. Calculate the minimum energy. Minimum energy means in the ground state. Ground state means we consider n is equal to 1. So the length of the box is given. Ground state is mentioned. So we'll use the formula E is equal to n square h square upon 8m L square and do the substitution directly. So if you have any doubt regarding these solving the numericals, I have already solved it in the video which is uploaded regarding the numericals on potential box. You can refer to it and understand the substitution and simplification. And also if you have to convert it into electron volt, we know that 1 electron volt is equal to 1.6 into 10 power minus 19 joules. So we'll convert these joules into electron volt and write it as 34.56 electron volt. Next one, an electron is bound in one-dimensional infinite well of width 1 into 10 power minus 10. So find the energy of the ground state and the first two excited states. So we have to find for the ground state also and the two excited states also. So let us see how we are going to do it. So the length of the box is given. We have to find for the first and the next two excited states. So we take first n is equal to 1, then 2 and then 3. What is the formula? N square h square by 8m L square. H is a constant, 6.625 into 10 power minus 34. M, the mass of the electron is constant, 9.1 into 10 power minus 31. And the width of the box is given 1 into 10 power minus 10 meter. So what is going to vary is with the value of n. So for the ground state, E1 is equal to n square h square upon 8m L square. This is the answer. And for E2, we consider n as 2. So 2 square will be 4. So that is the difference here. We are taking for n 2. So we get 2.412 into 10 power minus 17 joules. And for E3, the second excited state, it is n square is 3 square. So 3 square will be 9. So 9 multiplied by this value also you can do, or you can substitute here and get the value. So this is for the ground state and first excited state and the second excited state. One more last one. An electron is bound in one-dimensional box of side 4 into 10 power minus 10. Calculate the minimum energy. They have not mentioned what it is. Minimum energy is always in the ground state. So for ground state, we consider n is equal to 1. So this is the minimum application you should know. For ground state, the energy is minimum. So consider n is equal to 1. And the width of the box is 4 into 10 power minus 10 meter. And the formula remains the same. E is equal to n square h square by 8m L square. So just substitute for n square as 1 square. All other things are constant. Length is given. Substitute and simplify. And for simplification, you can use your calci. So while practicing itself, I recommend that you use your calci and be familiar with the functions so that it will become very easy for you in the examination. And also here we are doing the conversion to electron volt. So whatever we get in joules, we are converting it into electron volts. So I think with this we complete the discussion on the question bank of module 1. You can refer to these books also for theory, any clarification regarding the theory or the numericals. So thank you and see you again in the next lecture.
Like, share and subscribe. Hit the bell icon for more updates.